Hello, I'm Håkan Menlöv. I'm from the University of Birmingham, and there we're working on the silicon vertex tracker studies for a future EIC, so I'm going to talk about that a bit. So here's an outline of the talk. I'll start talking about the silicon vertex tracker, what it is, why it's important, and why we need it. And then I'll move on to talk about some simulations we do for it, which are to determine the geometric parameters of the silicon vertex tracker, such as the positioning of the sensors, the extent of the sensor layers, the pixel sizes, and so on. And then I go a bit more in depth talking about the pixel sensors, which are the parts that make up the silicon vertex tracker. And with the Rutherford Appleton Laboratory, we are working to develop a specific EIC sensor. So I'll touch on that a bit, and then I'll move on to the conclusions and outlook of the talk. So, the silicon vertex tracker, it's the innermost part of the detector. So here you can see a concept for BNL and a concept for JLab. And the thing I'm working on, the silicon vertex tracker, is the very innermost part of the detector. It's in the spread square, the most central part. And the nice thing is that for the work I do, the results will be useful for either detector concept with just slight differences. So, the silicon vertex tracker is the main detector for vertex position finding, and it also contributes to momentum measurements. So what we need is a very fine spatial resolution to separate the primary and secondary vertices. We need low material in terms of radiation length to reduce multiple scattering effects. The baseline used for these studies is the ALICE ITS upgrade, and we heard about that yesterday. And there, in terms of material, they have around 2% of X0 in the four innermost layers. And so we aim for this or better. So why do we need a silicon vertex tracker? Well, one thing is the open charm reconstruction. So the signature for charmed particles is a primary vertex and then a displaced secondary vertex. So for an example, if we create a D star in the collision, it will decay quite immediately to a D0 and a pion. And this D0 will then decay within around 120 micrometers into a kaon and a pion. So to be able to separate the charmed particles, we need excellent impact parameter resolution, and this is dominated by the position and the resolution of the innermost tracking layers. So we want to get as close as possible to the beam pipe and the highest possible spatial resolution. Now this is from theory. So we've done some simulations on this. The studies were made for a full silicon vertex tracker using EICUG. So EICUG is a specific simulation package for the EIC. It contains a particle generator, geon propagation through the detector, hit digitization, and track finding. The parameters of interest we looked at is the momentum resolution and the pointing resolution. Now the pointing resolution is related to the impact parameter. We looked at it in both the transverse and the longitudinal plane, but they follow the same trends, so I'll only present the transverse plane here. We've investigated different layouts and different pixel sizes. So here are some images from EICUG. What you see in blue is TPC, and the yellow and green parts are the silicon vertex tracker. And here's a zoomed-in view where you can see the layer structure of it. And the total radius of this opening in the TPC is 200 millimeters. So it's not a very big thing. It looks impressive here, though. So what we did was move the layers and change the pixel sizes, but we also tried adding a separate time-stamping layer to see how that would affect the resolutions. And studies have also been made at higher pseudo-rapidities, adding disks, and we'll get to that in a bit. So first of all, for the pixel size in the barrel, so here we see the relative momentum resolution to the left and the transverse pointing resolution to the right. And this is pseudo-rapidity between -0.5 and 0.5, so it's very central in the barrel region. And we see that the pixel size has no effect on the momentum resolution, and the pointing resolution improves with reduced pixel size. Now, this we knew from theory, but it's nice to see it pop up in the simulations as well. This is a quite low transverse momentum. Now this is at a pseudo-rapidity of 3, which is in the disk regions. This is with 7 disks. And what we see here, it's again relative momentum resolution and transverse pointing resolution. So both momentum resolution and pointing resolution improve with reduced pixel size. So for best performance, we've seen that we want to use small pixels located near the interaction point, which we've also seen from other layout simulations that I don't have time to show. So smaller pixels are better, so we want pixel sensors in the silicon vertex tracker, and this leads on to the rest of the presentation. So pixel sensors, they're made of silicon. There are hybrids and as monolithics. In hybrids, you can see a sketch here. The sensitive volume and the readout electronics are in separate chips, and then they are bonded together somehow, normally by bump bonds. So up until now, this is the most commonly used sensor in silicon vertex tracker. They're radiation tolerant and fast, but they draw a lot of power, which means they add a lot of material. Monolithic active pixel sensors have the sensitive volume and the readout electronics in the same chip, and are made using commercial CMOS technologies, and they're thin and have fine granularity, which is nice. A special case of this is the depleted monolithic active pixel sensors called DMAPs, and this utilizes high voltage, high resistivity CMOS technology, and the depleted means that the depleted volume is intended to be as large as possible. Now, this has some advantages. So first of all, compared to hybrids, DMAPs have lower costs. You can mass produce them in commercial CMOS technologies, which again is cheap, and it's also easy to manufacture loads of it. We will end up needing a few square meters at least. We also have a lower material budget, which reduces the effects of multiple scattering, and we avoid the bump bonding, which is complex and laborious. Compared to MAPs, the depletion in DMAPs gives us a faster, more uniform charge collection, which helps improve the signal. In Birmingham, we have a few test chips that we work with. These are of the type called the TowerJazz investigated chips. They're made in the TowerJazz 180 nanometer CMOS imaging process. Now they were originally developed for the Alice ITS, and this is the technology that's used in the LP chip as well. So this is a monolithic test chip, which has many different pixel flavors, like different pixel sizes, different charge collection electrode sizes, and different spacing between the collection electrode and the electronics. We have two process versions, the standard and the modified process. Here you can see the standard process on the left. And the important thing to note is the depletion region. It grows here from the collection electrode. Whereas in the modified process, a deep planar junction has been introduced that the depleted region grows from. So in this way, we can reach a higher depletion. So this is a DMAPS process. So the goal is to have a small collection electrode, which gives a low capacitance. And if you have high depletion, you can have smaller pixels, which gives lower noise, lower power. And also with depletion, the charge is collected by drift, which is faster. We made some measurements on this using an iron 55 source, and here are some results from that, comparing the standard and modified process. The modified process is in red, so here's the amplitude spectra. You can immediately see the K alpha and K beta peaks of the iron. This is for a 28 by 28 micrometer pixel. So, immediately we see that the modified process has a higher signal to noise ratio than the standard process. Looking at the rise times, we see that the modified process has a shorter rise time, so charge is collected faster. It's also a narrower rise time distribution, which indicates a more uniform charge collection mechanism, i.e. fuller depletion. Now, for a 20 by 20 micrometer pixel, the differences are smaller due to the relatively large depletion already with the standard process. You can think the depletion region remains the same size, but we shrink the pixel. For larger pixels and spacing, we've seen that the modified process shows worse performance than the standard process. We also have a chip that allows separate biasing of the P-well and the substrate, and the results are shown here. And what we see, quite unexpectedly, is that when we increase the substrate voltage, we decrease the signal-to-noise ratio. Now, naively, you would think that increasing the bias would make the charge collect better and faster, but we see that this is not the case here. And again, looking at the rise times, we see this again. So at the rise times at very high voltages, we get a widening of the rise time distribution, and it even goes to a sort of two-peak distribution. So increasing the substrate voltage decreases the signal-to-noise ratio, and increasing the substrate voltage also makes the rise time distribution wider. And this is due to smaller charges being collected slower, and smaller charges come from the pixel edges. So it's the hits between the pixels that don't get collected properly. And this leads on to the conclusions of the technology investigation. So we've seen that the modified process performs better up to a 30 by 30 micrometer pixel size thereabouts. Smaller pixels, there are smaller differences between the processes, and this again is due to the higher relative depletion already in the standard process. And higher bias voltage does not improve the signal, and this is due to the shape of the electric field, which has a minimum at the pixel border. So these results are consistent with simulations and published results from a similar sensor. And here you can see a TCAD simulation made by Magdalena Munker of CLIC. And the colors are the electrostatic potential and the electric field lines are drawn. Here you see the P well and 2 collection electrodes. This star indicates the electric field minimum I was talking about. So what happens when we get a charge between a hit between the pixels is that the charge drifts towards this field minimum, and then it slowly drifts towards the collection electrodes. So, and increasing the bias voltage straightens these lines out more, so we sort of slam more charge into the P well before we drift it along to the collection electrodes. So higher potential difference gives a longer path and a slower charge collection. And this is a problem, but it has been, some fixes have been proposed and they have been implemented in silicon in what's called the mini-multi chip. So these pixels have been modified to fix the problem at the edges. This up here, try to fix it by adding an extra deep P well on top of or below the already existing P well. And here is a gap in the N layer, and both of these modifications have the same purpose, sort of funneling the electric field towards the collection electrode. Now, this looks good so far. Analysis is ongoing of test beams of this chip, and the initial results are positive, but there's a publication, or several, in the works, so I can't present any proper results on this yet. But using the results from the sensor investigation, we're working with the Rutherford Appleton Laboratory to develop an EIC-specific sensor. And the goals of this is to develop, first of all, develop a high granularity silicon vertex tracker, but also investigating the feasibility of a time-stamping layer. So if we could timestamp every bunch crossing, that will help keep track of the polarization of an event. We want to see if this is possible. It's a feasibility study for now. So the challenges are the timing and the pixel size, and also keeping the power down. This power figure is from the Alice ITS, again, our baseline. So the pixel size we want is 20 by 20 micrometers or smaller. If we have a separate timestamping layer, we can go up to 350 in that to match the expected TPC resolution. The timing resolutions we need will depend on the site. So if it's a BNL, we need 9 nanoseconds, and if it's a JLab, we need 1 nanosecond. And the latest results we have is that we can reach a timing resolution of 4 nanoseconds using a constant fraction discriminator. Now, a CFD uses a lot of power, so it's not possible within the power budget to stick this in the small pixels, but if we have a separate timestamping layer, this would work. But anyway, this study is ongoing. They're doing it at RAL as we speak, and we have meetings with them every month. So it's exciting. So this leads on to the conclusions and the outlook of the talk. The results we have so far is that the simulation showed that we want a small pixel size and detector layers as close as possible to the beam pipe. The TauGS modified process suits our needs, but the sensor layout is crucial. We don't want this electric field minimum in the center, because that would, well, you saw it ruin our signal. Yeah? These extra modifications can potentially be beneficial, but it needs further investigation. The studies so far done on a 36 by 36 micrometer pixel, whereas we want a much smaller, and we've seen that things are a bit different when you go smaller. And current work that I'm doing is analyzing the mini-multi test beam data from one of the test beams. I'm also finishing up simulations of different detector layouts, focusing on the area encompassing both the barrel and the discs for now. The future work is, first of all, we'll continue the sensor development with RAL. That's ongoing. For the simulations, we'll move on to do full event reconstruction, investigating heavy flavor observables, so taking proper events and propagating them through the detector rather than single particles, which we've been doing so far. For the sensor part, we'll be doing tests of single photon avalanche diodes, SPADs. Now, SPADs are fast and have a fine granularity, but they're allegedly not radiation tolerant. So we're going to investigate this a bit. However, since the EIC is low irradiation, they might be a good fit for us. We will also do tests of the TauGS monopix chip from Bonn, which will arrive after Christmas, is the plan. So there's lots of exciting work ahead, and that concludes this presentation. Thank you. And that concludes this recording, I suppose. Thank you.